In this series, I'm going over every hard data analysis and problem solving question from the SAT. This is part 6, going over every hard question related to inferences from sample statistics and margin of error. Every question in this video will be 3 out of 3 difficulty, and again, the domain is problem solving and data analysis. The skill is inference from sample statistics and margin of error. Every question has a unique question ID. You can see it up here in the top left. If you look in the video description, all of those question IDs will be listed along with the timestamp of the exact minute and second where I start going over that problem and a brief description of the topic of that problem. Diving right in, we have this table. It has texting behavior, talks on cell phone daily, does not talk on cell phone daily, and then the total people in each row. So the light, texting behavior, medium, and heavy, and then total. In a study of cell phone use, 799 randomly selected US teens were asked how often they talked on a cell phone and about their texting behavior. The data are summarized in the table above, so this table here. Based on the data from the study, an estimate of the percent of US teens who are heavy texters is 30%, and the associated margin of error is 3%. Which of the following is a correct statement based on the given margin of error? So based on this margin of error, well, it means they're approximating it's 30% of just teens in general are heavy texters. And margin of error means it could be more or less than it by that percent. So it could be from 27 to 33%. So it would be something along those lines. Let's see. Approximately 3% of the teens in the study who are classified as heavy texters are not really heavy texters. Not necessarily, right? The margin of error means it could be down to 27, so that 3% of those 30 could be like up to that much within whatever, maybe some 99 or 95% confidence interval, doesn't say. But it doesn't necessarily mean 3% less. It could mean 3% more. It could mean 1% more. It could be exactly correct. Right? We don't know. It is not possible that the percent of all US teens who are heavy texters is less than 27%. Okay, well, margin of error, a lot of times in statistics, they'll be like, this is the margin of error with this percent confidence. They didn't say confidence here, so that might be with 100% confidence, in which case this would be true. I'm going to look at the other ones, because this does fit into this thing. It's like it's not possible that the percent is less than 27 because I wrote 27 as the lower end. But again, margin of error, like this doesn't mean it's exactly right in all cases. Like they would have to maybe specify that more, but if we can eliminate the other options, then this could still be our best one. The percent of all US teens who are heavy texters is 33%. We don't know that. It could go up to 33%, but no, we don't know that it is 33%. And it is doubtful that the percentage of all US teens who are heavy texters is 35%. Okay, I like that better because it says doubtful, right? Not possible. Because, usually with the sample, basically what it means is you're just taking 799 randomly selected, so you're hoping that they're going to be a representative sample of all US teens, right? But, there's always a chance that you randomly over-selected the heavy users or under-selected the heavy users based on just, a normal distribution of how people are. And if you just took 799. The bigger the sample size, the less likely, assuming that you are doing truly random sampling, the less likely that it will not be representative, and the more likely it will become more and more representative. But with 799, that's where they're getting the confidence interval from. And doubtful is a better way of saying it, right? So it's doubtful it's outside of this range because that's the margin of error. Because maybe they're saying like there's a 99% certainty or 95% certainty it's in this range, right? It's not actually certain. So not possible. I didn't like that to go from the get-go. But 35 is bigger than 33. It's outside of that range. So it's unlikely. It's very doubtful. Right? It's probably like a maybe 1% chance that that's true or less, depending on which of these confidence intervals it is. So D would be the best answer there. It is doubtful that the percentage of all US teens who are heavy texters is 35%. Another table here, views on nuclear energy use. Basically how in favor of them people are and the frequency of people asked, or frequency of respondents who answered that when asked. So it says, a researcher interviewed 411 randomly selected US residents, and asked about their views on the use of nuclear energy. The table above summarizes the responses of the interviewees. If the population of the United States was 300 million, it's more like 340 million, I think now, maybe getting closer to 350 million, when the survey was given, based on the sample data for the 411 US residents, what is the best estimate in millions of the difference between the number of US residents who somewhat favor or strongly favor use of nuclear energy. So that's one of the categories, is somewhat or strongly. So somewhat or strongly favor. And again, it's going to be in millions, compared to the number of those who somewhat oppose or strongly oppose. So somewhat oppose or strongly oppose. Okay, so we basically want to figure out like what proportion of them are this versus this. And then, or actually you don't want to do proportion. Yeah, I guess proportion of the total are somewhat favor, then what proportion of the total are somewhat oppose or strongly oppose. And then multiply that by this 300 million. And then you could get like the numbers for each, or the estimated numbers for each, and then you just find the difference between those two. All right, so we'd say we've got 56 plus 214 are the total that in some way favor it, either somewhat or strongly. And then we've got over here, it's 104 plus 37 are the ones that oppose it in some way, either somewhat or strongly. Now we have to put that over the denominator of the total. Unfortunately, they didn't give us a total row here, so we have to actually add them all up. But we technically only have to do that once, because we do 56 plus 214 plus 104 plus 37. So, I mean, you could do that without a calculator, but I've got one, so I'm just going to type it in. Once it's validating the OS, we've got 56 plus 214 plus 104 plus 37 gives me 411. Oh, wait, they did say that. Okay, I didn't even need to add those up because it's 411, but I guess this confirms that that is the number that's accurate for this table. They wouldn't give you a false one, though. So over the total like that, and then we can do 56 plus 214. There are 270 who are in some way in favor of it, and we could put that out of 411. And then 104 plus 37, that would be 141 out of 411. So that's the proportion. Now you could change that to a decimal or percent, it doesn't really matter, because ultimately we're multiplying it by 300 million. I'm just going to write 300m because we want our answer in millions. So we don't need to, write in all of those zeros multiplied by 10 to the 6th power. So 300 million times that, 300 million times that. So just do 300 times 270 divided by 411. That gives me 197.080292 million. And then we've got 300 times 141 divided by 411. Gives me, these are the ones who are opposed in some way, 102.919708 million. Okay, now I have to find the difference between those two numbers. So I'm just going to subtract the smaller one from the bigger one. And it gives me 94.16058397, And what do they say? Round to the nearest whole number of millions. So 0.1 will round down. It will just be 94 million is the difference between those two. 94. You don't have to write the million because it says how many millions. Just 94. And yeah, I mean, that makes sense. 197 million of the, we're expecting, based on this sample, 411, we're assuming it's a proportional sample, or we're assuming it's a representative sample of the population at large, and we're multiplying the proportion of the total that were surveyed, so 56 plus 214 out of 411, so 270 out of 411 were in some way in favor. So if that same proportion, which 270 over 411, that's 66%, a little bit less, so about 2/3 of people support it. That makes sense. This is close to 200 million out of the 300 million, and then this is close to 100 million out of the 300 million because it's about 1/3 of the people who were surveyed support it. So we assume it's also about 1/3 of the total population. Right, so that would be how you would do that problem. And you'll note I didn't round until the end. That's why I was writing out all of these decimals. It probably is not necessary to round like that or to go that far beyond what you're rounding to. But I don't like to round until the very end, right? Get what your answer is unrounded and then round that. Because sometimes if you round early, it throws off your answer by 1 or 0.1 or something like that. Probably didn't ultimately matter in that problem, but it's just a good habit to get into. Here we have another table. So there's sample A and B, and then percent in favor, margin of error. Let's see if they explain what those are. It says the results of 2 random samples of votes for a proposition are shown above. The samples were selected from the same population, and the margin of errors, or the margins of error, were calculated using the same method. Which of the following is the most appropriate reason that the margin of error for sample A is greater than the margin of error of sample B? Well, they're both random, and they're from the same population. They were selected from the same population. They were calculated using the same method. So they don't say that it's, when they say the same method and it's the same population, but it's not necessarily the same sample size from that population. So the larger the sample size, the lower the margin of error. Again, assuming that you are sampling that larger sample size equally, in an equally random manner that would give the same chance of being representative of the population. So if you have a bigger sample size, there's less likely that a few outliers will throw it off, or that you just happen to oversample one of the sides than the other by random chance. So if this has a lower margin of error, B, then that's probably a bigger sample size. And some of the other reasons they gave, it could have been a different population, or one of them more random while the other one's not, or a different method or something like that. But they eliminated all of those options here. So we don't have to worry about any of those possibilities. It's likely coming at a sample size. So bigger sample, or they might say that sample A is the smaller sample, so it has more opportunity for error, or could be thrown off more by an outlier, something like that. So let's see, sample A had a smaller number of votes that could not be recorded. Votes that could not be recorded. Did they say anything about that? Sample A had a smaller number of votes that could not be recorded. That would mean that more votes were recorded, assuming that they had the same sample size. So that's kind of the opposite of the truth. If they're not recorded, that would technically mean that A had more people respond, or that's what they're trying to imply. So it's not that, because A had the smaller sample, if anything. Sample A had a higher percentage of favorable responses. I mean, that's true, but that doesn't have anything to do with the margin of error. Right, so it's not that one. Sample A had a larger sample size. No, sample A would have to have the smaller sample size. That's why it has a larger margin of error. And sample A had a smaller sample size. That would be the answer, D. All right, so a larger sample size gives you more confidence in the data that you can extract from that. I mean, think of it, if you extend it to its extreme, right? If you only sampled one person, right, then you'll say, 100% of people are in favor of it, or 100% of people are against it, right? That's not accurate, right? 100% of people generally aren't going to be in favor of anything. I mean, there might be, I'm trying to think of an example, but, even if there's something like, do you want to eat ice cream or, bungee jump without a bungee cord or something, like there might be some people who would respond to that or something. So I would say if you have a sample size of 1, it is pretty much never accurate to the entire population. If you had 2, right, there's a very good chance that if you happen to randomly choose 2 people, they might both agree on that thing, even if the general population would not. Whereas if you sampled the entire population, then you have the exact right answer. If there are going to be like 10,000 people voting and you sample all 10,000 of those people, you already did like the vote. Or you already know where all 10,000 of those people stand. Now you could say it might not be accurate to election day because maybe people change their minds. That's fair, but this is going to be so remarkably close to what the actual thing would be unless there was some huge change in opinion. But in that case, right, this was still a 100% accurate reflection of the opinion at the time that it was taken, and then the opinion changed or shifted. So, think of it that way. Like if you have the largest possible sample, then it's 100% accurate. If you have the smallest possible sample, then it's definitely wrong. And you don't know how wrong it is, but the closer you get to that extreme of having everyone sample, that's going to get more and more accurate. At a certain point, it will get to a point where like it is diminishing returns. Adding more people to the sample doesn't really make it worthwhile. It's not going to make it necessarily higher confidence rate. But if the margin of error is small, that means there's a big sample. If the margin of error is bigger, that's a smaller sample. In State X, Mr. Camp's 8th grade class, consisting of 26 students, was surveyed, and 34.6% of the students reported that they had at least 2 siblings. So at least 2, that means they could have 2, 3, 4, 2 or more. You could write 2 plus. The average 8th grade class size in the state is 26. If the students in Mr. Camp's class are representative of students in the state's 8th grade classes, so they are a representative sample, or it says if they are, and there are 1,800 8th grade classes in the state, which of the following best estimates the number of 8th grade students in the state who have fewer than 2 siblings? So fewer than 2, that would mean they have either 1 or 0. And yeah, so that would be the ones it would be the complement of this, right? So if 34.6% have 2 or more, then everyone that's not in that category would be 100 minus 34.6%. or 100% minus 34.6%, which would be, what is that, 65.4%. So 65.4% would have one or fewer. I feel like that doesn't seem accurate to me. I would think, I mean, having taught most of my students, oh, I guess number of siblings, right? So it's number of siblings. So that actually is accurate then, yeah. I was thinking at first like they're only children or no, but yeah, obviously if it's the number of siblings, then the number in the family is one more than that. I did have a lot of students who had one sibling. But okay, so about 2/3 have either 0 or 1. And, oh, they want an estimate of the number of students who have that. Okay, well, it is a representative sample, so we can apply this to the population at large for our estimate here. And there are 1,800 classes, that's this thing. And each class, or not each class is 26, but the average class size is 26. So you can multiply that by the number of classes, so we'll get the number of students. So 1,800 classes times an average of 26 students per class gives us 46,800 eighth grade students. And then you multiply that by this percentage. So multiply it by 65.4%. So times 65.4 divided by 100, or you could just do times 0.654. 46,800 times 0.654 gives us 30,607.2. So it's going to be something close to that. They round to the nearest 100 students, so it's 30,600 students would have fewer than 2 siblings, so either 0 or 1 siblings. Right? That would be how you would do that. And we could figure out how many total students was the 46,800. And just to make sure it makes sense, is that about 2/3? Yes, because it should be a little bit less than 2/3 of those students who have either 0 or 1 sibling. We have a table of poll results, looks like some kind of election. The table shows the results of a poll. A total of 800 voters selected at random. So at random, that implies it's likely going to be a representative sample if it was truly random sampling, and well done. So a total of 803 voters selected at random were asked which candidate they would vote for in the upcoming election. According to the poll, if 6,424 people vote in the election, by how many votes would Angel Cruz be expected to win? All right, so we're just assuming that this random sample is representative of the population as a whole, and we want to know how many votes, or by how many votes would Angel Cruz be expected to win. So we need to figure out how many votes is Angel Cruz expected to get and how many votes is Terry Smith expected to get, and then find the difference between those two. All right, so Angel Cruz is expected to get the same proportion, so 483 out of the total who were polled here, and it says there were 803 polled. You could add these up to confirm that, but they do add up to 803. So we multiply that by the number of people expected to vote, or it's saying if that many people vote. So 483 over 803 times 6,424. And this will give us the expected vote breakdown, assuming it's follows the proportions of this poll. So 483 divided by 803 times 6,424 gives us 3,864 votes for Angel Cruz. And then the expected vote for Terry Smith would be 320 out of the total, which is still 803, times the number of people who are expected to vote, 6,424. And we just do 320 times 6,424 divided by 803. See, I changed the order there. I multiplied first, then divided. It doesn't matter, right? Because the commutative property of multiplication, dividing by 803 is the same as multiplying by 1 over 803. So you could change the order, you multiply them, same thing. This gives me 2,560. So that's how many votes are expected to come for Terry Smith based on this poll result. And now we just find the difference between these two. And we've got 1,304, which would be option B. So Angel Cruz, if 6,424 people vote, and if this poll is exactly representative, then he's expected to win by 1,300 votes, about 1,304. Oh, and that's the end. All right, so those are all of the questions that are hard difficulty, specifically in the inferences from sample statistics and margin of error. So it doesn't seem like there are that many concepts you need to know all of the hard questions in this set, but just make sure that you master them all. It's pretty much just an understanding of the statistics. There's not too much involved math here. I mean, you've got like these things where you have to figure out what proportion would either vote for this or fall into this category, and then multiply it by the population at large. And then I think this is the second one that they did this, where you had to find the difference between the two proportions when applied to the general population. that math itself is not too hard. It's more about, can you conceptualize this and figure it out and then do that math correctly. And then we've got, this one, again, you're just multiplying that percentage, which you have to find it by doing the complement of the percentage they gave you. So make sure you know that. Right, if there are two options that add up to the entire thing, like if there's only 2 people you could vote for, and then you're pulling only people who are actually going to vote, then the total percentage of the votes should add up to 100%. Whereas if there were 3 candidates, right, then you'd have to add up all 3 to guarantee that you're getting up to 100%. And then this one, you had to figure out how many students there were by multiplying 1,800 times 26. So that was, I guess, the thing that made this hard versus medium. But, that's not too involved. Just make sure that you're comfortable with doing that and that you wouldn't just rush and go, 1,800, 8th grade. It says 8th grade classes, and the class size is 26. So sometimes they do give you information you don't need. So, watch out for red herrings. But it seems like in this category, most of the stuff they gave you was useful. Some of the stuff on the table was, just filling out the table. You didn't actually use each element in the table. But, just be mindful. If they give you something, it doesn't guarantee that you have to use that thing, but they probably gave me this for a reason, or think about what could this be used for, even if they're trying to lead you astray. Just make sure you understand the point of giving you that information. And we've got this one, the sample size. So this is just an important concept to understand, not just for the SAT, but in general, understanding statistics, understanding different, research findings and things. If you have a bigger sample, assuming that you have the same method of collecting the data and interpreting it, and that the samples are both representative, or at least both equally randomly selected, then a bigger sample will decrease the margin of error, whereas a smaller sample increases the margin of error. And when I went over that, when I talked about you can extend it to the extremes of, if you had surveyed everyone, the entire population, then it's going to be super accurate or 100% accurate. And if you had surveyed just 1 or 2 people, it's going to be much less accurate, right? Because either then you're going to get 100%, 50%, or 0. This one was another one where you had to, find the proportion based on the table, the values in the table, and then multiply it by the population at large, and then find the difference between them. So, very similar to that last question. This one is just important. I think some people might choose B if they don't fully understand margin of error. Margin of error does not mean it's guaranteed to be within that margin of error, right? It's not like it's 100% certain it's in that margin of error. It just means, based on whatever certainty they needed, certainty threshold they needed, it has to be in there. So maybe it's you have 99% confidence or 95% confidence or something like that. Whereas doubtful is a better way to say this. It's doubtful that it's outside of that margin error. Because that doesn't mean it's impossible. It does happen where, something outside of the margin of error, or something that's, a huge anomaly occurs. Things that are 1 in 100 chance happen all the time, but they're just a lot less likely than something that's within that margin of error, assuming that it's calculated correctly. And that's it. Okay, so just, make sure you understand how margin of error works, that you could set it up like this. So if you had, it's 30% is the value they find, and then you had to use the margin of error to subtract it from the expected value and add it to it to find this range of values that you are expecting to get. And then again, just know that's not a guarantee, it just is doubtful that it's outside of those. Okay. And yeah, so this video, I know there weren't that many problems in this set, but hopefully these descriptions were very thorough and that you got some value out of them. If you have any questions or comments, or if you have a correction or concern or anything like that, please leave that in the comments below. Appreciate any feedback. Like and subscribe if you found this video valuable. That will mean that you're going to get promoted more math content, more SAT content, maybe even more of my videos in your feed if you tell the algorithm that this is something that you like. And besides that, thank you for watching, and good luck with your test preparation.